So L'Hopital's rule is in 4.4, I believe.
Yeah.
So let's take a look. 4.4. Okay, can you give me your problem?
Yeah, I think it was. The limit as x approaches 0 from the right for 2 of x plus 1.
Say it again. Sorry, Danya. Can you say it again?
Yeah. It's the limit of x as it 0 or x as it approaches 0 from the right, and then in parentheses 2x plus 1 to the exponent of cotangent x.
Yeah, remember that this is the procedure in which you have to denote this. Because this approaches 1, and cotangent from the right of 0 is, so this is cosine over sine, right of 0, both are positive, so it's 1 to infinity. So you have to denote it by y, then you have to apply natural log, so you have cotangent x times natural log of 2x plus 1, and then you have to apply the limit to both sides. So the limit of natural log y as x approaches 0 from the right is limit as x approaches 0 from the right from this, cotangent x natural log of 2x plus 1. 0 from the right, this will be 0, and this is infinity. So we are happy. Why am I happy? Because always the product is easy to handle with a simple algebraic manipulation. So this is limit as x approaches 0 from the right. Natural log, do not move that anywhere. There will be a mistake. But cotangent is basically 1 over tangent, right? So cotangent is 1 over tangent.
Okay.
And at this point, I will plug in again. So this is indeed 0. And this is indeed 0 because it's sine over cosine, and sine is 0. Cosine is 1. So this is 0 over 0. And from here, I can use L'Hopital's rule. So always when you change it into a product, you know you're close to changing into a 0 over 0 or infinity over infinity. So the numerator differentiated is 1 over 2x plus 1, also multiplied by 2, the inner function prime. And this is secant squared. And nothing here is undefined anymore. So the top when x is 0, the top is 2. And the denominator when x is 0, the bottom is 1. So this is 2. Now you have to copy the beginning, and you have to copy the end separately. So this is limit of natural log y from when x approaches 0 from the right, and that is 2. And at this point, you swap. And you have natural log of the limit of 2x plus 1, I'm replacing the y, raised to cotangent x, as x approaches 0 from the right, is 2. Well, this must be e squared. E to the second power equals this. So then you can go back and write that this is e squared. So that's my concern that I would like to express. If you redo the problems we do in class, you will get a much better understanding before you attempt homework. That's just my suggestion. Every brain works differently. So whatever works for you, I'm fine. But I recommend redo the problems we did in class first, so you know what's happening step by step, and you will feel much better, I think. You let me know. I may be right, I may be wrong. Maybe I'm right for some, maybe I'm wrong for others. Other question? Yes?
It's not saying that 2 is right.
I didn't say 2. I said e squared.
Oh.
I never said 2.
Wait.
How can it be 2? So natural log of e squared is 2. Natural log of 2 is not 2.
Because 1 divided by a secant squared of 0. Alright. So that's just e squared.
So when you swap the operators, you have the natural log of the limit equals 2. This limit must be e squared.
Oh, okay.
Only natural log of e squared will be 2. So that's why I went back to the original limit that he gave me, and I wrote e squared.
Got it.
So 2 is the natural log of your limit. It's not your limit. The limit of the natural log is 2, but this is not what we are looking for. That's why you have to swap the operators, and you write that the natural log of whatever is 2. This whatever must be e squared. Nothing else fits. The base raised to 2 equals this limit. But the base is e, we don't write it. E squared is this limit. We had in the lecture probably at least 4 of these. I highly recommend we do those as practice to feel better about it. Good. Other questions? Is there anything else? Do you have anything else for me? You can stop me anytime. Major topic. Major topic, and the applications are, we used to do the part of the application, some of the applications in Calc 1, but some years ago we moved them to Calc 2. So chapter 6 will be applications of integrals. Areas, volumes, arc length, surface, other things. Okay. Before I even talk about this, you can forget about it for a while. We're going to look at a function, very simple function, like x squared, and a very nice interval, let's say 0 to 2. And let's suppose the question is, find the area under f of x equals x squared between 0 and 2. There are several possibilities. First of all, to find the exact area, no clue yet. No clue how to do it yet. If you ask me at this point to find an approximate area, I will say that's possible. With what we know so far, we can. And we can use 3 different methods. There's more than that, but for now, we only look at 3. Using leftmost point. Using rightmost point. Using midpoint. And you can say, what is all this all about? Okay, so let's take it slowly. Let's graph and see what happens. So first of all, here's the graph. 1 and 2. I want to go to the next page. Not enough room there anyway. I was going to go to the next page in the next second anyway, so I'd rather do it now. So again, this is a function f of x equals x squared. The interval is 0, 2, 0, 2. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. So here's the graph. And we're asked to determine this area? We don't know how to determine the exact area yet. We will very shortly, but right now we are asked to approximate. Let's suppose we start by using, we want to use, number one, 2 subintervals. And we want to use the leftmost point. Okay, I will divide the interval into 2 equal length base rectangles because we are using the leftmost point. So the first rectangle has the height of the leftmost point, but there is no height. This is 0. So the area of the first rectangle is 0. Base times height, but the height is 0. I move on to the next. This is the height because I'm using the leftmost point. And this is the area of the second subinterval. So the area with 2 left, or it doesn't matter, you can invent, I don't know, area left 2, whatever you want to write it. It means the area calculated with the leftmost point with 2 subintervals. This is approximately base times height, but the length of the base or the width of the base is 1, but the height is 0, f of 0, plus length of the with the width of the interval, which is 1 again, of course, multiplied by the height, which is f of 1. My calculation, so f of 0 is 0, this is 0, plus 1 times f of 1 is 1. So the approximation or the approximate area using 2 subintervals with the leftmost point is 1. Is this an overestimation or under? Grossly underestimate, because I did not include this area and I did not include this area. Underestimate. Let's also see how it looks like with R2. I have to graph it again. 1, 2, 1, 2, 3, 4. The graph again is this. And now I want to use still 2 subintervals, but using the rightmost point this time. This is the height. The height now is the rightmost point. Rightmost point, of course, for the height. Base times height, and this will be this interval, this area of this rectangle. The next base, this time the height is at the rightmost point, so this will be the area. So the area with R2 is approximately base times height, 1 multiplied by f of 1 plus base times height, 1 times multiplied by f of 2. Well, 1 times f of 1 we already know is 1, plus 1 times f of 2 is 4, so this is 5. Now, at this point, I'm going to ask again, is this an underestimate, overestimate? Of course, it's an overestimate because of these pieces, which are not under the graph. So this is an overestimate. Where is the true exact area between those two? Sure. The exact area is definitely less than or equal to 5, but definitely more than or equal to 1. Now, let's also look at the midpoint. How do I determine the area, so-called M2? Okay, so this is the base of the rectangle. Right in the middle, I draw the height. And then at that height, I create the rectangle. The same here in the middle, I draw the height. At that point where it touches or crosses the function, I draw the horizontal, and I get that rectangle. So if this is 0, 1, and 2, this is 0.5, and this is 1.5. So the area with the midpoint and 2 subintervals will be base of the rectangle, 1, times f of 0.5, plus base of the rectangle, 1, times f of 1.5. So f of 0.5, basically plus, so 0.5 squared and 1.5 squared. 0.5 squared plus 1.5 squared. 2.5. This will always be the case. Is this an underestimation or an overestimation? I'm not really sure. If you look at my graph, you may say it's an under. I don't know. My graph is far from being exact, but definitely the midpoint formula will give us, will be anywhere between the left and the right. Not always the left or the right will be higher. It depends. If the function is decreasing, it will be the other way around. So, but it definitely is somewhere between the lower bound and the upper bound. Okay, here's my next question for you. Let's suppose we used, in this case, we used 2 subintervals. For simplicity, we're never going to use 2 subintervals, but the reason why I wanted to use 2 subintervals is because it's easier to explain what I'm doing. But now if I increase to 4, I will have 4 areas. I will divvy up into 4 equal subintervals and determine the leftmost point, rightmost point, or midpoint. Do you think that the area with 2 subintervals, the approximation with 2 subintervals of the exact area, or 4 subintervals will be better? Anyone?